Let's look at some simple methods of analysis. For example, determination of time of death. This is often done simply by the temperature of the corpse. The body cools off at a reproducible rate of 1 to 1.5 degrees Fahrenheit per hour. Although you've got to appreciate that this is going to be skewed by the temperature outside, what kind of clothing they have on. To make it a more, I guess they used to do anal probe, yuck. So now they do liver probe, and that being in the inside of the body is less susceptible to fluctuation. But here we go. Let's use a little bit of the chemistry we've seen. For example, we talked about pH when we talked about acid rain. Well, the blood has a slightly basic pH. It's 7.5. And this pH begins to rise after 2 hours of death. So what happens is the rise in pH, which they can measure from the blood, taking blood samples, but the muscles begin to get taut. And remember what this is called? Rigor mortis. Rigor mortis is a phenomenon, rigor mortis, body rigid, and the stiffness becomes very pronounced over the next 12 hours. And then 1 to 2 days later, the pH drops again, the body loosens up. So if you find a cold, dead body that is loose, death probably occurred more than a day before. How about the last meal? Sometimes they will go through the stomach contents to figure out where the person was or what the person was doing in the last few hours of their lives. As we noticed in the nutrition topic, saliva contains enzymes. Remember, those are biological catalysts. A catalyst increases the rate of a reaction, how fast a reaction occurs. And just as you put stuff in your mouth and start to chew it and introduce it to the saliva, it starts to break them down. In fact, if you chew crackers, you'll start to notice they start tasting less starchy and more sweet. This continues in the stomach, then the small intestine. But remember, those 3 polysaccharides we looked at, one of them, cellulose, does not get digested. It goes through your whole GI tract pretty much intact. And it is very useful for identification. Plus, when you die, there's a little valve that closes permanently between your stomach and the intestines, so the stomach contents can give them clues to the time of death. The degree of digestion, indigestible particles, and you know what? This is even called forensic botany, and this woman, Dr. Jane Bach from University of Colorado in Boulder, she has done a lot of work on this, and she can identify things such as pineapple, kidney beans in dead bodies. So if you're dining out with a potential murderer, you may want to consider a Mexican restaurant with pineapple upside down cake for dessert, so they can trace your whereabouts. Now, for both alcohol, drugs, poisons, the most state-of-the-art analysis will involve spectroscopy or spectrometry, and that is the interaction of light with matter. Radiation. They'll impinge light on atoms, molecules, materials, and watch for changes in their energy, and that is recorded. Chromatography, this is gas chromatograph. Chromatography means the writing of colors, chromo and graphy. This is a coupled analytical technique often used in crime labs. And again, here we are at the Columbus Crime Lab, and they are the workhorses of most crime labs. Let's see why. All right, chromatography, a method. The importance of chromatography, and remember I told you I would put in red what I need you to know for the final. A lot of this is in detail, but I do want you to know this. Chromatography is a method for separating mixtures, and Mother Nature abhors pure substances, so most everything we come across is going to be a mixture. It's based upon the fact that we introduce 2 phases. The components, where can you see this? Let's see. How about something this simple? If you tape a paper towel and write on it. Put some ink on it, and then dip it in water. You've probably done this inadvertently, but the mobile phase is the water. The stationary phase is the paper towel. And what we'll see is a separation of the ink components. Ink is made up of multiple dyes, and they will travel at different speeds up the stationary phase. The stationary phase often is now a thin coating on the walls of a sample compartment. More sophisticated, I guess. The mobile phase can be a gas or a liquid, and then it's allowed to, the mobile phase is flushed through the reaction vessel. A small amount of suspect substance or unknown material is dissolved in a solvent and then injected by needle into a hollow tube. We're talking specifically about a gas chromatograph now. A flow of inert gas propels the mixture through a coated coil glass tube. In this case, the glass tube is the stationary phase. And the longer the tube, the more sensitive the instrument. They coil it so they can get, sometimes I've heard they've had a mile of this glass tube. The chemicals in the mix migrate over the sticky stuff, if you will, on the inside of the glass tube. Since each element moves at its own speed, it crosses the finish line at different times, and this helps us to identify them. A highly sensitive computerized detector at the other end will identify the sample. Comparison or control substances are also put through the chromatograph, and this helps identify substances. So they'll look at, for example, an accelerant on a piece of charred wood against, the comparison would be wood without the accelerant. Gas chromatographs can be used to identify many things, from poisons to drugs to explosives. It's used a lot for blood alcohol evaluations. It's very fast, very clean, very good. And there are different types, depending upon the phase, that is, gas, liquid, solid, of the sample, how volatile it is, how easy it is to handle. But the gas chromatograph, that bottom one, is the workhorse of the analytical lab. Okay, now once you've separated them, you can try to identify them, but sometimes that's not going to happen, especially if you really don't know what you're looking for. And then you will couple it with a mass spectrometer. And I need you to know what a mass spectrometer is. It identifies molecular mass of an unknown chemical. It also will help identify can give the abundance, the relative abundance. A chemical in the mix, in our mixture. Okay, so it not only identifies, it also tells you how much, gives you an idea of how much is there. Chemical compounds are hit with electrons. That makes them charged ions, breaks them into fragments, and then because they're charged, they are susceptible to a magnet. The magnet deflects these ions onto a bent path, like around an S-curve on the highway. And the amount that's deflected, the extent of deflection, depends upon how much these guys weigh. The heavier they are, the more massive these ions, the less the deflection. All right? It identifies, the mass spectrometer identifies the exact molecular mass of an unknown chemical and its concentration by this degree of inflection. And you can change the strength of magnetic field, you can accelerate it, you can slow them down, you can do all sorts of changes to the conditions, so that sometimes you can get to the point where you can detect extremely small, well, I'm sorry, when I say sometimes, I mean one of the good things about this guy is, and it's not sometimes, it can detect extremely small traces of individual chemicals. If you have a huge magnet, and I've seen magnets that are meters, okay? These instruments can cost up to $750,000 to $1 million. And they're usually, when they're this kind of sensitivity, this kind of intensity, they are used for more research, in more research environments than in crime labs, because they usually don't, in the research environment, especially in like OSU chemistry department, they're trying to find brand new molecules, brand new chemicals, and in a crime lab, they really are looking for many of the same things over and over again. So they don't need that kind of costly sensitivity. Here's a picture of both of them. Here's the top one is a gas chromatograph, and like I say, the flow control, this is the inert gas that pushes through my sample. I bring my sample in here, my unknown, or whatever I need to identify. I bring in an inert gas like N2 or helium, something like that is not going to react with him. And then here is my hollow tube, coated with a sticky stuff. How about coated with a chemical that'll cause it to absorb. And then adsorption. It's not absorbed, it is on the surface. So it stays on the surface, and it will take it, it'll have different reactions to this adsorb. So different components of the sample will travel through these coils at different speeds. And then you've got a detector and recorder. The mass spectrometer, you have your sample coming in here. The ion hits it. It makes it, these are my different ion fragments from my sample. And they all have charges now. And you can see they're different sizes. They go through a magnet, and the larger guys will be deflected less than the lighter ones. And they can then discriminate between the different components. Okay, that'll do it.